A very happy evening to you all and welcome you all to the third keynote of today's World Space Week celebration. Well, we are celebrating World Space Week 2020, and how can we miss out any topic on astrophysics? We have been talking a lot about satellites now, but let's explore something about interstellar medium. Why explore? Why do we want to know more about interstellar medium? To answer that, here today we have with us Professor Jayanth Murthy, a very eminent personality in the field of astrophysics. He is a research scientist at the Johns Hopkins University Department of Physics and Astronomy. He's currently working on many projects, including the Galax diffuse data and also projects related to low altitude space payloads. He has specific interest in space missions, interstellar dust, and diffuse radiation field as well. It is a great pleasure to invite Mr. Professor Jayanth Murthy here on screen to dedicate a keynote to all of us on interstellar medium. I welcome you, sir. The screen is yours.
Okay, thank you. You're going to share my screen now, right?
Yes, sir.
Okay, great. All right, so what I was asked to talk about is the interstellar medium. And this is actually a fairly detailed subject. So I'll go a little bit into the physics. And I'll try to keep it fairly simple, fairly understandable. If you have any questions at the end, please do ask. So the first, let me just see why. Okay. Right. So the first question we have to ask is why we want to study the interstellar medium at all. What is the interstellar medium? So the name tells you what it is. Interstellar means between stars, and matter, medium, that's the stuff that's in between stars. It's both gas and dust. And when I say dust, I don't mean the kind of dust that you find in your house, but this is interstellar dust. The interstellar medium is about 15% of the mass of our galaxy, 15% of the mass of any galaxy. Of that 15%, most of it is gas, and only about 1% of that 15% is in the form of interstellar dust. And to put this in perspective, this is much less matter than any place that we might consider on the Earth. So typically when you look at the density in the air in our room, for instance, you think of something like Avogadro's number, 6 times 10 to the 23rd atoms per cubic liter or whatever it is. But in space, we talk about something as about densities closer to 1 atom per cubic centimeter, even as low as 1 atom per 1,000 cubic centimeters. A really dense region in the interstellar medium might be as much as 10,000 atoms per cubic centimeter, nowhere near Avogadro's number. So when we look at the interstellar medium, we look at different forms of it, and I'm going to show a few pictures. This is the Veil Nebula, which is a supernova remnant. You get the Horsehead Nebula. This is, again, another supernova remnant. So you get some of the most beautiful pictures in astronomy are from the interstellar medium. So when you say, why do you study the interstellar medium? Well, the basic answer is because it's there. And this goes a little bit into why we do science at all. Why do we do basic science? Really, the interstellar medium, studying the interstellar medium is not going to help you in your daily lives. It's not going to get you a better phone. It's not going to help you get a bigger car. But what it is it's a part of the universe. And we cannot understand the universe unless we understand the interstellar medium. As I said, on a purely prosaic level, most of the pictures that you see from astronomy are actually pictures of the interstellar medium, just because the pictures are so good looking. But why do we study it? We study it because it's there. And I think, is my slide not moving? Nikita, are you there?
Uh, Sir, your slides are it's stuck in the first slide.
Yeah. So why is it not moving?
Could you start your screen share again?
I will do that. Maybe I will try it like this. No, that's not it either. I shared my screen, but sharing my screen didn't seem to work. So let us try. Okay, are you seeing it now? No, it's still stuck on the first slide.
Yep.
I don't use StreamYard much. So let's try one more thing. No. Okay. Let's try one more thing. Maybe. Okay.
Uh, is it possible to scroll the screen and use it in the same mode?
Yeah, let's try this one more time. Okay, now you're seeing it.
Yes, sir. Yeah.
Okay. All right, let's do it this way. You can't see it's not full screen, but that's okay as long as it works. Okay, right? You can see it fine.
Yes, sir. Perfectly fine. Yeah.
All right, let me show one of my nice looking pictures. This is a supernova remnant, and when you look at it, you get a sense that there's actually something very active there. It's not when you think of space, you think of something that's very quiet, very peaceful. The stars are there. The stars have always been there. The stars will always be there. But now, when you look at a picture of something like this, you see that a lot of activity. It's clear that there's been explosions. Things are happening everywhere. Space is really a very active place. So now, uh, when we look at the interstellar medium, where does it come from? Well, everything comes from the Big Bang. So, what happened at the time of the Big Bang? The Big Bang produced only hydrogen, helium, and a very little bit of lithium. There were no metals. And when astronomers talk about metals, we mean anything other than hydrogen and helium. Oxygen is a metal, iron is a metal, zinc is a metal, chlorine is a metal, everything. So, but in the Big Bang, there were no metals formed. So immediately after the Big Bang, maybe even within 100 million years after the Big Bang, the first stars began to form. And these were huge stars. Uh, there were maybe 100 solar mass stars. So they formed within 100 million years. They would go through all their fusion. You would get first hydrogen would form helium, helium would form carbon and nitrogen and oxygen, and then you get all the way up to iron. Once you get iron, then you can't go any higher, and so then you get a supernova explosion. And so once these big stars explode, then they seed the interstellar medium with metals, and you get a new generation of stars forming. with more and more metals. So you get this constant cycling between stars and the interstellar medium. Stars are formed out of the interstellar medium, and then once the stars explode, or maybe from stellar winds, as they expel their outer atmosphere, they enrich the interstellar medium with more and more of these metals. So, in a very real sense, we're nothing but stardust. We're nothing but interstellar medium because we're made up of things like carbon, oxygen, nitrogen. Where did these elements form? They all formed in supernovae. So we're nothing but stardust. Now, when you look up in space, most of what you see is stars. You look at bright objects, and so you see stars. But there's as I said, there's a lot of matter between the stars, and that's what we're really interested in now, the interstellar medium. And so, how do we observe this matter? How do we observe the interstellar medium? Well, one way to observe it is from line emission. So, what is line emission? It's when you have a gas. That gas is excited, and I'll show you what happens. But the gas is excited, and once it's excited, it gets de-excited. It goes back to a lower energy level, and it emits radiation. So when I look at something like this planetary nebula here, this is the Ring Nebula. At the center of the Ring Nebula is a white dwarf. That white dwarf is putting out lots of ultraviolet radiation, and that ultraviolet radiation is exciting the gas, which is then re-emitting light. And so the different colors tell you the different elements that's there in this planetary nebula. So what you're really looking at here is a red giant, a star like Betelgeuse. So Betelgeuse is now a huge red supergiant. Eventually, that star will, or maybe more like our sun. As our sun gets older, eventually it'll become a red giant. The outer layers of the sun will expand out, while the inner core is left as a white dwarf. And so what you'll be left is an outer atmosphere that eventually expands out into the interstellar medium and becomes part of the interstellar medium. So that's what you're seeing there. Now, what do I mean when I say that the lines are excited? So the easiest way to explain this is with the hydrogen atom. So if I look at the hydrogen atom, I think you've all learned this in school. You think of a Bohr atom, where an electron is orbiting a proton. And what was Bohr's insight? It was that the energy levels of the electron were quantized. So the electron could be in the ground state, or the first excited state, or the second excited state, or the third excited state, and so on. It couldn't be at the 1.5 excited state. So the energy is quantized. It can only be at certain energies. So if I look at the interstellar medium at general, all of the atoms are in their ground state. They're all unexcited in the n equals 1 state. This is not true if we look at the gas in our room. If we look at the gas around us, that follows a Boltzmann distribution because the atoms are always colliding. But that's because there's so many atoms per cubic centimeter that there's enough atoms that they can actually collide. But in space, there's so few atoms that the atoms just never collide. So the only way for the atoms to de-excite is by radiating this energy. And so if an atom is in its ground state, it'll stay in its ground state unless a photon hits it and kicks it up to one of the higher energy states. Now, these photons for the hydrogen atom have to be ultraviolet photons, because that first energy level, n equals 2 to n equals 1, is already at 1200 angstroms, which is far into the ultraviolet. A star like the sun doesn't put out much ultraviolet photons, so we won't get any radiation from the interstellar medium around the sun. But if you're around a white dwarf, now that white dwarf is a hot star, a temperature of maybe 30,000 degrees, so it's pumping out lots of ultraviolet photons. And so you get those, the hydrogen atom will be excited to higher energy levels and will then re-radiate this energy. Now, if that photon excites it from n equals 1 to n equals 2, then the only thing that can happen is that the photon comes back down to its ground state, n equals 2 to n equals 1. And so that then gives you another, what's called a Lyman photon. Nothing exciting. The photon goes up and it comes back down. The only thing is that if I'm looking at a star through this gas, that photon is essentially removed from that light that I see. So when I look at the star, I'll see an absorption line. That hydrogen atom will absorb the photon from that star, and then it'll re-emit it in some random direction. So as far as I'm concerned, that photon is lost. Now, if that photon goes up to the n equals 3 state, now there's two different ways for the photon to come back down to the ground state. It can go from the n equals 3 to the n equals 2, in which case I get a bomber photon in the visible. So when I look at interstellar space, I see a lot of red radiation. And that red radiation, most of it is Balmer alpha. It's from the n equals 3 state to the n equals 2 state of hydrogen. Or it can come directly down from n equals 3 to n equals 1, in which case I get a Lyman beta photon that'll go off and excite another hydrogen atom. And so on, n equals 4, n equals 5, and so on. And eventually I'll get a photon with an energy, with a wavelength of 912 angstroms or shorter. And that will that will completely dissociate the hydrogen atom into an electron and a proton. And this is true of more complex atoms. If I get oxygen atoms, then there's just so many more lines, and these will radiate in different wavelengths. Now, if I look at a simple, if I were to think of this as what I would say is that the n equals 1 to n equals 2 state, that's a single energy. So the photon has to have a wavelength of exactly 1215.67 angstroms, or else that photon would not be absorbed because the energy levels are quantized. But we know that in nature, nothing is a delta function. Everything has some width to it. And this is true of these absorption lines also. So if I'm looking at an absorption line from the interstellar medium in a star, it will have a width. Now this width comes from two things. One is what's called a Lorentzian energy, a Lorentzian broadening. And that's basically just the uncertainty relationship. Normally, you think of the uncertainty relationship between position and momentum. So P times X is less than H bar by 2. But there's an equivalent relationship between energy and time. So the longer lived a line, the longer that line stays, the more stable that line is, the more precisely its energy is defined. If it's a very short-lived line, then there's a corresponding width in the energy. So what the effect is that if a photon comes around and is a little off of the line, the uncertainty relationship will tell you that you don't really know what the energy of that photon is. So maybe it can still be absorbed by this atom. And so that gives you a natural line width, a Lorentzian line width. Now, the other thing that happens is that whenever you're looking at absorption in the interstellar medium, you're not looking at only absorption from a single atom, but rather you're looking at absorption from a cloud of atoms. You're looking at absorption from an ensemble. So some of the atoms will be moving towards us, some of these atoms will be moving away from us, some of them will be moving at cross angles. And so there'll be a thermal broadening also, which will be Gaussian, because these velocities will be distributed according to a Gaussian. A Gaussian is just a bell curve. It's basically anything that you get in statistics is eventually a Gaussian. So you get two curves. You get a Lorentzian curve based on the atom itself, on the properties of the atom. And on top of that, you get this Gaussian curve, which is based on the velocity distribution of the interstellar gas. And the convolution is a Voigt function. So I put the equations there, but don't worry about it. The basic thing that you need to know is that the Lorentzian curve is much shallower. Here I've shown an emission line. An absorption line is just the emission line flipped over. So the Lorentzian is much shallower, but has broad wings. A Gaussian is much narrower and falls off very rapidly as you go to further and further away from the line center. The Voigt profile is the convolution of the two, and so it looks like a Gaussian in the center. And as you go off to the line edges, you get closer to the Lorentzian. And so now if I look at a real absorption line, this is an absorption line against a star. Why is it an absorption line? It's because the interstellar medium is dark. So the only way for me to observe it is against a bright object. So I'm looking at a star. This particular star is beta Cas, and I'm looking at the Lyman alpha line. And so what I see is I see the hydrogen line in the center, and on the wings of the hydrogen line, I see the deuterium line. You see the deuterium line is much narrower than the hydrogen line. That's because there's much less deuterium than hydrogen. So why is the hydrogen line so broad? It's because there's so much of it. Why is it? And so what happens when you look through a lot of matter? It's like looking through table tennis balls at a wall. If you have one table tennis ball, then it'll block so much light. If you have two table tennis balls, it'll block twice as much light. 10 table tennis balls, they'll block 10 times as much light. But as you add more and more table tennis balls, eventually they start blocking each other. And eventually, finally, you'll get to a stage where you have so many table tennis balls that it blocks the wall completely. And then no matter how many more balls you add, you just can't block any more of the screen. And so that's what's happening to this hydrogen line in the center. You've added so many hydrogen atoms that you've blocked all the light from the center of the line. And here are some other lines. Here's carbon lines here. This is neutral carbon. This is 3 times ionized carbon. Here's neutral magnesium. And here's ionized iron. So you see that these lines are all much narrower than the hydrogen line. Why are they narrower? It's because there's so much less of any element than hydrogen. Hydrogen is 90% of the atoms by number, 75% by mass. So wherever you look in the interstellar medium, you'll see lots and lots of hydrogen. Everything else is mixed in with the hydrogen, but you'll see less of it. And so when you're looking at these lines, what you can do is you can say how much of that element there is. So depending on how deep the line is, you can say that, okay, if it's really deep, like hydrogen, for instance, there's a lot of it. If it's not so deep, like this carbon line here, then maybe there's not so much carbon there. Or maybe it's a weak line. And then based on the width of the line, if it's a very hot line, if the carbon is very hot, then you can say, then it's moving very fast, so the line will be broader. So based on the breadth of the line, you can say how hot it is. Based on the depth, you can say how much of it there is. And depending on the redshift of the line, you can say whether the interstellar gas is coming towards us or away from us. So you can see that from these interstellar absorption lines, you can see how much of the gas there is, how hot it is, and how fast it's moving towards us or away from us. So we put all of this information together, and we can get a picture of the interstellar medium. Even though we can't observe it directly, by looking at all of this secondary information, we can try to get a picture of what the interstellar medium looks like. And so what we've done here is this is a picture of what we call the very local interstellar medium. So we look at the absorption lines towards nearby stars. Here's Alpha Centauri, which is about 4 light years away. Sirius is maybe 5 light years away. Procyon, Altair is maybe 10 or 15 light years away. And so as we look at these different stars, we see different amounts of absorption. So when we look towards Alpha Centauri, we see so much absorption. And we say, okay, there's so much gas between us and Alpha Centauri. If I were to look at Capella, which is off towards Alpha Centauri, but much further away, I'll still see about the same amount of absorption. So I'll say, okay, there's no gas between Alpha Centauri and Capella. If I look towards Procyon, I see maybe less absorption. So from all of this, I'll say that the sun is near the edge of this local interstellar cloud. I told you that you can measure the velocity of the interstellar cloud. So I put all of these velocities together, and I find that the velocity of the cloud is in this direction, this arrow here. Unfortunately, you can't see my mouse. So it's in this grayish arrow here. That's how the interstellar cloud is moving. The sun itself is going around the center of the galaxy. And so the sun is going off in this direction, this yellow arrow, at a velocity of about 200 kilometers a second. But this cloud is moving off in this direction with a velocity of about 20 kilometers a second. And so, what effect does this have? Well, there's some speculation that, for instance, if you look back to the Greek time, they say that Sirius was a red star. Now, we know that when we look at Sirius now, it's one of the brightest bluish white stars in the sky. So how could it have been a red star? Well, one possibility is that as this interstellar cloud is moving, maybe it moved such that there was a little clump of that cloud between us and Sirius. And as I'll show you later, maybe there was interstellar dust in it, and maybe that made Sirius a red star 2,000 years ago. Or maybe the Greeks maybe it's just a mistranslation of the Greek. Whatever it is, here it is, we're in the middle, or we're near the edge of this interstellar cloud. And as time goes along, over thousands of years, the cloud is moving down, we're moving off to the left, and so we'll be eventually out of this cloud completely. Just outside the cloud is this black region, which is empty. Inside the cloud, the density is maybe an atom per cubic centimeter. Outside the cloud, the density is an atom per 1,000 cubic centimeters. Inside the cloud, the temperature is about 5,000 degrees Kelvin. Outside the cloud, the temperature is 1,000,000 degrees Kelvin. And all of this we get, or most of this we get from absorption line measurements. Some of it we get also from things like X-ray emission. So now if we look at a slightly more larger picture of the interstellar medium, we find that the previous picture was maybe 5 parsecs across. Here we're looking maybe 200 parsecs across. Here's the sun again. and the sun is still moving around the center of the galaxy, 200 kilometers a second or so. And now you see that here's this local interstellar cloud, and here is that vacant region, very low density region, where the density is an atom per 1,000 cubic centimeters. And here's this orange are various molecular clouds, where the density in those molecular clouds is maybe 1,000 atoms per cubic centimeter, or even 10,000 atoms per cubic centimeter. And these molecular clouds is where new stars are being formed. So if we look at this larger picture of the interstellar medium, what we say is that the interstellar medium is divided into more or less three phases. One is the cold neutral medium, and these are these giant molecular clouds. One of the most famous pictures from the Hubble Space Telescope, and this is what I told you, most of the most beautiful pictures of that you see from astronomy are actually pictures of the interstellar medium. So what are we looking at here? Here's the Eagle Nebula, and this is huge molecular clouds, giant molecular clouds with maybe 1,000 solar masses or even more. The temperatures in these clouds are as low as 20 degrees in the center, maybe rising up to 100 degrees near the edges. The density is maybe an atom per cubic centimeter near the edges and as much as 1,000 atoms per cubic centimeter near the center. But these don't occupy very much of the volume of the galaxy, less than 1% of the volume of our galaxy. And so these are the regions of star formation. This is where new stars are being formed in our galaxy. So if I look at the Eagle Nebula, I see these red dots here. These are not actually red stars. They're actually hot blue stars that only look red because we're looking at them through so much dust. So these are stellar nurseries. The molecular clouds are where new stars are being formed. Then outside of these giant molecular clouds, you get the warm neutral medium and the warm ionized medium. And this is like the cloud that our sun is in, that local interstellar cloud. A temperature between 1,000 and 10,000 degrees, an atom of density of maybe a tenth of an atom per cubic centimeter, all the way up to maybe 10 atoms per cubic centimeter. And this is maybe 20% of the volume of our galaxy. And finally, you get the hot ionized medium. And this occupies most of our galaxy, maybe as much as 70% of our galaxy. The density here is maybe an atom per 1,000 cubic centimeters. And the temperature is 100,000 to 1,000,000 degrees Kelvin. So when you look at this hot ionized medium, what you see is because it's so hot, it emits at high energy. So you see it in X-rays and you see it in highly ionized gas. So that is the gas. I'll separate this into two phases, the gas and the dust. As I told you, the interstellar medium, you see it's comprised about 99% of it is gas and about 1% is dust. But the dust is very important and it's very visible. And so if you look at something like the center of our galaxy, if you look at the disk of our galaxy, you see these dark patches. Now, in ancient times, they thought that these were just dark patches in the galaxy. After all, the stars, who knew how the stars were distributed? So we'll just say, okay, there's no stars there. Now we know that there are no stars there because something is blocking the light of those stars. So if I look at this dark patch in the center of in the disk of our galaxy, this dark patch here is the Coalsack Nebula. Why is it called the Coalsack Nebula? It's called the Coalsack because it's so dark. It doesn't allow light through it. Now, the difference between gas and dust is that gas is one atom or maybe a few atoms. The dust is maybe 50 atoms, which might be a large molecule, up to micron-sized particles. So when the light interacts with interstellar dust, I told you that when the light interacts with interstellar gas, it's largely quantum effects. That means that it interacts, that what you see are transitions between one quantum state of the atom to another quantum state, from, let's say, the n equals 1 to the n equals 2 state. So that means that these are all lines, absorption or emission lines. But when light interacts with interstellar dust, that's more of a solid state effect. The light interacts with the entire dust grain. So what you see is that the photon is absorbed by the dust and is then re-emitted as thermal emission, as blackbody emission. When the photon is absorbed by interstellar gas, it absorbs it as a line, as a photon, and then it re-emits a photon at either the visible or the UV. Either, let's say, n equals 1 to n equals 2. You get a Lyman photon in, you put out a Lyman photon, or maybe you get something like a Balmer photon or a Paschen photon or something. But it's always a photon. When the dust absorbs, it re-emits as thermal radiation, again as photons, but now you get infrared photons rather than UV or visible light photons. So these this interstellar dust, it absorbs in the visible and the ultraviolet, and then it re-emits that energy in the infrared as thermal emission in the infrared. So if I were to look at that Coalsack Nebula, that same dark region in the optical, that it looks very dark because I'm seeing it against the background of more distant stars in the plane of the galaxy. But when I look at it in the infrared, I don't see the stars because the stars are much hotter, and so they don't have much black body emission. But the dust is now re-emitting all of that energy that it absorbed in the optical and the UV back out in the infrared. The dust may be at a temperature of 20 degrees or 30 degrees Kelvin, and so it's re-emitting that energy in the infrared. Now, if I were to look at our galaxy, what I see in many of the wavelengths is actually gas and dust. So if I look at the very longest wavelengths at radio, I look at emission from molecular gas. As I go down to shorter wavelengths in the infrared, what I see is largely dust emission. And then if I look in the optical, I'll see that the dark regions in the optical are the bright regions in the infrared, because the dust is absorbing the light in the optical and then it's re-emitting it in the infrared. I can also see the light in dust scattering. So the light from bright stars hits the dust, and then the dust will scatter some part of it back to us. When I look at interstellar dust, I've told you some different ways of observing. One is through this infrared emission. Another is through UV scattering. But most of the information that we know about interstellar dust comes from the extinction curve. And so what is the extinction curve? It's the amount of light absorbed by the interstellar dust. So when I look at this curve, I see that it looks a little odd. The x-axis is inverse wavelength in microns. That means that the longest wavelength, the infrared, is off on the left-hand side. The shortest wavelength, the UV, is on the right-hand side. And because it's a log plot, the UV is spread over a large part of the x-axis. On the y-axis, it's essentially a measure of the amount of absorption. So what do you see from this curve? You see that very little energy is absorbed in the infrared. Very little energy is absorbed in the infrared. A lot of energy is absorbed as you get to shorter and shorter wavelengths. So now the way this presentation of the plot makes sense. Why have we spread out the UV? It's because most of the action occurs in the ultraviolet. So we want to spread out that information so that we can get more detail. We don't care much about the infrared because there's not much happening in the infrared extinction curve. So now what can we say from this extinction curve? Well, as you see, there's very little absorption in the infrared. And what that tells you is that the dust grains are about the same wavelength as that infrared emission. They're about a micron. The largest dust grains are about a micron in size. Why does it tell you that? It's because the light doesn't interact with particles that are much smaller than it. So if you're looking at radio waves are much bigger than people, so they don't really notice people. So as you get to longer and longer wavelengths, the light just doesn't notice the dust. So the largest dust grains must be about a micron in size. As you get to smaller sizes, there's more and more absorption. So there's more and more dust as smaller grain sizes. And when you get to the smallest grain sizes in the UV, what you see now is that there's lots of absorption. And so there's lots of grains at the very smallest sizes. So you get few grains, few large grains, and lots of small grains. And these smallest grains, how large are they? Well, they're as small as maybe 50 atoms. Large, as I said, large molecules. Now you see this big feature here at about 2000 angstroms. And this is called the 2165 angstrom bump. So what does this tell you? Well, it tells you a lot about what's in the interstellar dust. Because this feature is so prominent, whatever is causing it has to be something that's quite common. It can't be hydrogen, it can't be high helium because there's no lines of hydrogen and helium, but it can't be uranium either because it's so strong that there's just not enough uranium in the universe to give you such a strong feature. So we look at different things. What could it be? It could be carbon, magnesium, silicon, iron, only a few things. And when we look at all these different things, we see that there's a feature in graphite that is similar. You know, graphite, like in your pencil lead, the reason your pencil lead works is because the graphite slides off your pencil lead in sheets. And so this absorption, this feature corresponds to that 2165 angstrom feature. So people think there's lots of interstellar graphite in space. All right. So now, when we look at when we try to see what interstellar dust is made out of, it's hard for us to measure the dust directly because we're only looking at things like the interstellar extinction curve. But what we know is that if we look at a volume of space, then we know that the volume of space is comprised of stars plus gas plus dust. And the stars are a snapshot of the interstellar medium at the time of formation of that star. So the sun was formed 5 billion years ago. So it's a snapshot of the interstellar medium 5 billion years ago, except that, of course, the sun has had nuclear fusion, so we've formed more and more helium in the sun. If I were to look at an O star, these O stars are much younger, 10, 20, 30, maybe 50 million years. So if I look at an O star, it's a snapshot of the interstellar medium only 50 million years ago. So the sun is old, an O star is young, and so we get samplings of the interstellar medium at different phases. Now, when we look at the interstellar gas, I showed you how you could look at absorption lines to look at the gas. We look at different atomic and molecular lines, and we get an estimate of what's in the gas now. So we can say there's so much carbon, so much iron, so much magnesium, and so on. And so now we get a sampling. We look at the star, we see what the interstellar medium was like then. We look at the gas, we see what the interstellar medium is like now. And so the missing part, whatever is missing between the gas and the dust, between the gas and the star, must be an interstellar dust. So this allows us to look at the composition of the interstellar dust. And when we do that, what we find is that, as makes sense, the harder an element is to evaporate, the more of that is missing from the interstellar medium. So if I were to look at something like nickel, there's a lot of nickel that's missing from the interstellar medium. So where is it? It must be in the dust. So as we look at more and more refractory metals, elements that are harder to evaporate, more and more of that is in the form of interstellar dust. We can also look at interstellar emission lines. So if we look at Orion in submillimeter, what we see is this bottom spectrum here. So what does that look like? We can look at a sample of the air. In this case, the upper graph is a sample of air in Los Angeles. And so it looks very similar. So what does that tell us? Well, it tells us that there's lots of cars going around in Orion, or maybe more realistically, that the gas in Orion is very similar to the gas to the pollution in Los Angeles, which is basically incompletely burned hydrocarbons. You have lots of petrol from all the cars and buses and lorries and so on, and so the gas or the dust in Orion must be very similar to that. And what is that? That's basically benzene rings. They're called polycyclic aromatic hydrocarbons, and it's benzene rings of greater or lesser simplicity. So now when we try to put all of this information together and we try to say, okay, what is an interstellar grain? Where are interstellar grains formed? We know that interstellar grains are not formed in the interstellar medium. Why is that? It's because the density is so low that you just cannot get enough particles together. Even a small dust grain of 50 particles, you just cannot get 50 particles to collide and give you a dust grain, not within the lifetime of the universe. So where do the dust grains form? Well, they must form somewhere where the density is a little higher, but the temperature can't be so high that the grains are destroyed. So you can't have these dust grains formed in the insides of stars. So where can they be formed? Well, maybe in the outer atmospheres of red giants like Betelgeuse. The temperatures are a few hundred degrees, 500, 600, 1,000 degrees Kelvin. So not so hot that you evaporate everything completely. The densities are fairly high so that you can get lots of collisions. And so maybe you can get dust grains formed. So what are these dust grains? Well, maybe they're more refractory elements, things like nickel, things like magnesium. These are formed, and the silicates, iron, they give you this refractory core that can survive at a temperature of a few hundred degrees Kelvin. Now, this grain then goes out. It's kicked out by the solar wind, or eventually on the death of a star. You remember the Ring Nebula? It goes out and forms the interstellar medium. So these dust grains go out and become part of the interstellar medium. Eventually they cycle through the galaxy, maybe 50 million years or so, and they come into these molecular clouds. Molecular clouds, the density is higher, they're protected from radiation, and so now you can start to get things forming, things condensing on the outer layers of this refractory core. And so now you get ices, not water ice, carbon dioxide ice, carbon monoxide ice, methane ice, and so on, ammonia ice. So you get this mantle that's comprised of ices. And maybe if you're in a very protected environment, like in the center of a molecular cloud, maybe you'll get organic molecules or organic compounds forming. So things like amino acids, maybe even simple RNA there. So you get more complex things forming. You might consider something like a fractal dust grain. Now, what's the difference between this and this? This and the previous one. Here you get a very compact dust grain, not much space. Or you might get a dust grain that looks like this with a much more fairy castle structure. Maybe one dust grain comes in, hits another dust grain, and you form this fairy castle type structure. The difference between this and the previous one is there's a lot more open space. So maybe dust grains are some combination of this. We just don't know. So let me end my talk with this slide. And this is the Horsehead Nebula. So what are you looking at here? Here you're looking at some reflection nebulae here. You have lots of dust around a star. So you're seeing scattering from the dust that's around that star. This red emission here is this bomber emission from hydrogen. So you have all this UV emission from Orion that's exciting the gas and that's emitting this emission. Here's the Horsehead Nebula. And when you look at this picture, you see lots of stars on the top, not many stars on the bottom. So that tells you there's lots of dust in front of this, in front of all the stars. And when you look at it with that perspective, this Horsehead Nebula is just a projection of this dust here in front of this gas. So it's blocking the gas here, and so dust down here, gas here, and the bright stars up here. So you see all of the different aspects of the interstellar medium in this one photograph of the sky. So let me end here, and happy to take questions.
Thank you so much, sir, for that wonderful keynote session on interstellar medium. We learned quite a lot about how the dust particles and the other gases in between the star spaces cause the reddening effects and the extinction effect. And on that, I have a query regarding how do we predict whether there's going to be a star formation in an interstellar medium based on the density of the interstellar gases in a given region?
Okay, so how does a star form? Let's go to the basics. A star is big. A star is a solar mass of our sun, whatever it is, 2 times 10 to the 30 kilograms. I don't even remember the number. So anywhere from a tenth of that to 10 times that. So you need lots of matter. How do you get that much matter? Well, you can't get it in the general interstellar medium. So the only way you can get it is in those giant molecular clouds, like the Eagle Nebula. So how does a star form? Well, you get you get some sort of gravity enhancement. This cloud, things are moving around, and eventually you'll get a concentration of matter, and that starts to accrete more and matter around it. Eventually it accretes so much matter that you get fusion starting, and you get the star forming. So once you get the star form, that gives you shock waves. So those shock waves travel through that molecular cloud, and they compress more matter around it. So those sites of that compression may give you new star formation. So that's why you may get many stars forming together. One star forms, it triggers more stars forming.
And regarding the pillars of creation image, we see that the dust columns are raising in a straight column there. So you were talking about the formation of accretion disk for the stellar formation, like for the star to form. Why do we see a straight column there instead of gases coming together in a spherical formation? Instead of that, we see a vertical column there. Is there any specific reason for it?
Yeah, when you look at molecular clouds, these giant molecular clouds are typically gravitationally bound. But when we look at them, you have to remember that we only see a two-dimensional view. So how are they actually done? They won't be exactly spherical, of course, because there's all sorts of Uh, there's all sorts of gravitational effects on them. It's not like a star. A star is a very concentrated gravitational body, and so it's spherical. Here, the matter is so spread out that there's nothing to really govern its shape. You'll get bits sticking out like this Horsehead Nebula here. You get planes. You get different projections, so we see it at different angles. So it's very hard to predict what it'll look like. So the Eagle Nebula, it's these projections of gas out from what I guess another molecular cloud below.
Uh, and as far as my learning goes, that almost all the interstellar medium, they're inhomogeneous in composition. That is, we don't find any uniformity throughout its spreading. So, is there any way to that astronomers use, astrophysicists use to measure an average density of the interstellar medium or interstellar cloud?
I mean, when you say inhomogeneous, everything is inhomogeneous at some scale. Stars are inhomogeneous. You get a star. So you look at the galaxy and you look at it at different scales. You will always see structure. So everything that you look at is averaged. So when I look at a whole galaxy, I might say there's an average amount of gas. There's 1 atom per cubic centimeter in that galaxy. But as I start to look at it more and more detailed, then I will see structure. I will see inhomogeneity. If I look at the interstellar medium here and I look at it here, there will be differences. But what we try to do is we try to derive a coherent whole from all of this.
And regarding the reddening effect caused by the interstellar medium, is there any way or a technique that we can use to counteract this reddening effect so that we get the original image of the background stars as if the interstellar medium was not present?
So when most people are interested in things like stars or galaxies or quasars. So really, what they want to do is they want to remove the effects of interstellar dust. So what we do is we try to get the properties of the interstellar dust, and these people try to take out the properties of the interstellar dust. So what we do is we try to understand what that dust looks like, and then they try to use that understanding to get a better picture of what that more distant object looks like. The problem is just what you said. The interstellar medium is not homogeneous. Maybe if I look here, it's different from what I look from when I look there. So I try to derive an average interstellar extinction. But when they try to apply that interstellar extinction to any specific object, that may get complicated.
And those wonderful images of Horsehead Nebula and Pillars of Creation in the Eagle Nebulae, they were taken by Hubble Space Telescope. Now that Hubble Space Telescope is about to retire, is coming to an end on its service, we have James Webb's Space Telescope that is up to go to space now. With respect to that, what are your views on having space telescopes and their scope in astronomy?
Well, the James Webb won't actually replace Hubble because much of the capability of Hubble is in the optical and the ultraviolet, whereas James Webb is largely an infrared mission. So it will do things like find planets. It'll do things like look at distant objects. It won't do much. It won't get you pictures like this picture of the Horsehead Nebula, which Hubble got. So when I think about space observations, we do need a number of space observatories at all different wavelengths. We gain much information from that. We need observatories on the ground also, because you can always build bigger and better instrumentation on the ground as opposed to space. You can't imagine putting a 30-meter telescope in space. So we need a combination of things. And the more you have, the better it is for science.
Thank you so much, sir. That would be with the Q&A session, and thank you so much for telling us more about interstellar medium. I hope everyone enjoyed the session, and we are glad to have you here, and we would be hoping to have more and more sessions from you. Thank you so much for joining us. Okay. So on that note, we'll be ending today's keynote session on interstellar medium. It was a wonderful session, very informative by Professor Jayanth Murthy. And before I leave, I want to give you all a reminder kind of thing. We have started our online classes back again on SSERD. So we have topics related to space math at beginner and advanced level. We have life beyond Earth. We have space exploration and rocketry related courses available here on the website. So it is suitable for students who are above the grade of fourth. So I request you all to go to the SSERD website and give a look, have a look on all these courses. And thank you all for joining in today for the keynote session on interstellar medium. World Space Week celebration was, I mean, this particular keynote session was a gem on this our celebrations keynotes. So I thank you all for joining in again. This is Tejas KB signing off.